Hello, my name is Joe Darcy. I work in Oracle's Java Platform Group, and I'm talking today about what every Java programmer should know about floating point arithmetic. And if you have any questions during the talk, just drop them into the chat. Now, as a final warning, this is a talk about floating point arithmetic. To many people, floating point arithmetic is similar to spiders, a topic best left to someone else. So thanks for coming out here today. I hope you have more knowledge about floating point after the session. An outline of the rest of the talk, after some background, we'll go through a condensed floating point primer, how to understand the floating point approximation, and then give a few concrete lessons about how to use floating point in your everyday programming. What is floating point anyway? Floating point arithmetic is a systematic approximation to real arithmetic, useful in performing calculations on computers. Real arithmetic defines a set of values, the real numbers, as well as operations on those values. Arithmetic operations like addition, subtraction, multiply, and divide. Floating point arithmetic approximates both the set of values and the properties of those operations over those values. Now, why do we need to use an approximation? There are many reasons, including that exact results can get very large very quickly, and often exact inputs aren't known. So in doing many kinds of scientific calculations, approximation is necessary. Why does floating point have such a bad reputation? Before the IEEE 754 standard came into force in the mid-'80s, every architecture had a different floating point arithmetic, and there was a lot of variation, and it was hard to get cross-platform portability. But that standard was widely adopted, and the IEEE 754 standard has been revised and kept current over the decades. It's very commonly seen. The 32-bit float and 64-bit double types we have in Java correspond to formats defined in the standard. And there's a very straightforward default behavior. For the arithmetic operations, the floating point result closest to the exact mathematical result is the one that's returned. However, there are some factors that do contribute to this bad reputation. One is for any binary floating point system, 1/10, 0.1, is a repeating fraction in binary. So what you see is not what you get. A lot of the issues with floating point relate to decimal to binary conversion issues. Another factor is that the usual arithmetic properties, such as associativity of addition, don't hold. Usually, it doesn't matter what order you add things up in, but it does for floating point operations. In fact, floating point summation is still an active research topic in the scientific computing community. The semantics of a given language or VM might have a non-obvious mapping from operations within that language to the IEEE 754 operations. Now in Java, we do have a tight mapping from the language and virtual machine operations to IEEE 754, so that's less of an issue there. All right, now we can move on to the condensed floating point primer. First, we'll do a speed run of the different mathematical systems we've used, starting with counting and ending up with what we use in calculus. In the beginning, we just start counting with positive integers. Soon on, we move to addition. Once we have addition, we then add the inverse operation of subtraction. And once we have subtraction, to be able to subtract any two numbers, we have to add new kinds of numbers. We have to define negative integers and 0. Moving on from addition and subtraction, next we have multiplication. And again, we see when we introduce an inverse operation, in this case division, we get new kinds of values when we combine all the old values together. So with division, we add rational numbers, otherwise known as fractions. Now, rationals aren't sufficient to talk about all the mathematical structures we have of interest. So even if we want to do something simple, like talk about the diagonal of a square, so the diagonal of a square with sides of 1 is square root of 2, and square root of 2 is not a rational number, so we need something else. What we need to talk about diagonals in this case are called algebraic numbers. Those aren't enough either, because if we want to talk about the circumference of circles, the circumference of a circle is 2 pi times the radius, we need a different kind of number still. We need real numbers. And real numbers are kind of complicated. They can be decomposed in a few different ways: rationals and irrationals, algebraic and transcendental numbers. And it's a lot of work to formally define real numbers, but they're kind of the minimum mathematical object needed to have many useful properties, such as completeness. Fortunately, you don't need to understand the proofs and formulas and defining real numbers to use them. They are easy to use. And as a note of interest, there are other kinds of numbers too mathematicians use in other settings, like complex numbers you might have seen in certain engineering courses, and there's even structures called surreal numbers. So to recap, there are different numbers used in different contexts, from counting through calculus, and those number systems grow more complex to handle more situations and to handle more concepts. And while real numbers are complicated, they're as simple as needed to do the task at hand. Now, rational numbers, real numbers, and algebraic numbers do have something in common. They're all mathematical objects called fields. Fields are just the formal mathematical name for following the usual rules of arithmetic. For example, fields are closed under addition. If you add any two members of a field together, you get some other member of the field. And fields also have associativity of addition. It doesn't matter what order you add up different elements, you'll always get the same result in the end. And there are similar properties for multiplication, zero, and so forth. Now, these field axioms are the basis for, say, optimizations a compiler might do. And these are also the basis for algebraic transformations you might make during proofs or different ways to write a program. So with that as background, what are floating point numbers? What finite values can we represent as floating point numbers? So the structure of a floating point number is a sign times a significand times the base raised to an exponent. And we can categorize the IEEE 754 floating point values by the exponent range the format has, as well as the significand width. So specifically for the 32-bit float format, we have 8 bits for exponent, and there are 24 precision bits. That corresponds to about 6 to 9 decimal digits. For the 64-bit double format, there are 11 exponent bits, and there are 53 precision bits, and that's equivalent to about 15 to 17 decimal digits. So you'll note the double format has both more precision and a larger exponent range than float. So for a binary floating point number in particular, now we have the significand times 2 raised to the exponent. Now there is a constraint that the leading digit, B0, has to be 1. We call that normalized, and that just imposes a unique representation on the value. So based on this structure, we can see that binary floating point numbers are sums of powers of 2, where the ratio between the largest and smallest component is bounded because there's a limited precision, limited width to the precision field. So concretely, float and double are still fairly large. So let's look at a toy floating point format instead. So let's have only 3 precision bits and 3 exponent values, -1, 0, and 1. So 0 is a special case. So let's look at the smallest defined value here, 1/2. So one way to understand how this value comes about is that it's 1.00, or 1, times 2 to the -1. 2 to the -1 is a half, so this is 1 times 1/2, or 1. Another way to look at this would be to look at 100 as a bit string, where the 1 corresponded to 1/2, the first 0 corresponded to 1/4, and the second 0 corresponded to 1/8. So this interpretation, we would have 4/8, or 1/2. So the next value, 100, that's binary 5, so 5/8, 110, 6/8, 111, 7/8, and so forth. So these are all the combinations for when the exponent equals -1. So now we increase the exponent to 0, and instead of dealing with eighths, we deal with fourths. We have 4/4, or 1, 5/4, 6/4, 7/4, and finally, we increase the exponent again to 1, and instead of fourths, we have halves. So we have 4, 5, 6, 7 halves instead. That's what the values look like when we have 3 bits of precision, but we can have more bits of precision. So let's say we add a 4th precision bit. Now we start out with all the same numerical values we had under 3 bits of precision by adding a trailing 0, as you can see here. Then we have another set of values where the trailing bit is 1 instead. So that has the effect of inserting a floating point value between each of the existing values. We can also look at these values graphically. For p equals 3 on the number line, we have the values where the exponent is -1, 0, and 1. And we can see the numbers are getting more spread out as the exponent increases. Now you'll note there's a much larger difference between 0 and the first representable number than between the first and second representable numbers. That's a bit of a problem for computation, so we actually fill that region in with a special kind of value called subnormals. Now we'll have p equals 4. We have all the p equals 3 values, and then we insert the values in between there, and so forth. So these are all the finite p equals 3 and p equals 4 values. So we can write these down. We have the normal values, and now we have those new subnormals. And we can see for the subnormals, they're 1/8, 2/8, and 3/8, the same spacing as the smallest exponent. So there are only a finite number of floating point values, and we saw all the positive ones written down on the previous slide. So there's 16 of those non-negative values, including the subnormals. That means if we want to return a finite non-negative answer, we have in this system, we have to choose one of those values. So what values can we choose? Well, 1/2 and 1 1/4 are values in the system. We want to add them together, and the exact value is 1.75. Now, 1.75 is one of our representable numbers, so we should return that. But there are many cases where we combine two values in the system and we don't have that exact result defined. So if we want to add 2 1/8 or 1 1/8, we don't have those values defined. So we need some rule to help us when we don't have the exact value already defined. And that rule is called a rounding policy. A rounding policy is a function that maps from a real number to a floating point value in a given format. What it looks like is that there's a continuous segment of the real number line that gets mapped to a single floating point value. A representable number gets mapped to itself. In the Java programming language, our default policy used for most every operation is called round to nearest. Under round to nearest, the representable floating point value nearest the infinitely precise mathematical result is the one returned. Now, if you're exactly halfway between two representable numbers, then the one you return is the one with the least significant bit 0. So let's see what that looks like. We have the real number line up top, and then we have the floating point values at the bottom. And to make it clear that we can only return those floating point values, we'll remove the number line on the bottom. So let's first look at the region around 2 1/2. So if we're between 2 1/2 and 2 3/4, the nearest floating point value is 2 1/2. So in that case, we should round down to 2 1/2. So all the values in that region get rounded to 2 1/2. Likewise, if we're a little bit less than 2 1/2, say between 2 1/4 and 2 1/2, we should round up to 2 1/2 because that's the nearest value. Now we can follow the same argument for all the other floating point values shown here, and that gives us this diagram like this, where there's these little triangles around each number. So concretely, we have our examples from before. If we take 2 1/8, we can see this would round down to 2. If we have 1 1/8, that's halfway between 1 and 1 1/4. If we go look to the listing of the values on the right-hand side, we see 1 and 1 1/4 listed out, and the least significant bit of 1 is 0. That means in this case, we should also round down to 1. Now, the region we've drawn around 3 1/2 isn't symmetrical. We only have rounding up, but it seems reasonable that we should also round down with the same width of rectangle from 3 3/4. Now, that does still leave a question about what we should do for values larger than 3 3/4. Let's say we add 2 and 2 together with 4, what should we do here? So it seems this is a case where we'll have to expand our floating point approximation to cover more values, and we'll get to that in a minute. But first, we'll say a little bit more about the rounding policy. What are the benefits of this round to nearest rounding policy? This is close to the grade school rounding we're used to using. It does reduce round off error, and the detail about how ties are handled avoids drift in certain loops. So let's consider again the case using the toy format with 3 bits of precision. We added 1 plus 1/8 together, and we got 1 as a result. If instead we were using the toy format with 4 bits of precision, if we added 1 and 1/8 together, we could return the exact result 1 and 1/8, because 1 and 1/8 is a value that's representable in the 4-bit system. This is an example of a more general phenomenon we see with floating point, which is that usually using a more precise format gives you a more accurate answer. Precision is a measure of how fine a distinction you can make, and accuracy is a measure of error. So to measure error, you have to have some notion about what the right answer is. Now, another consequence of what we've seen with how rounding works is the following. Say, again, when we get back to using the toy format with 3 bits of precision, if we take 2 and 1/4 and add them together, 1/4 will get rounded away and we'll get 2 back. What that means is if we have the compound expression, 2 plus 1/4, do that, we get 2. And then we add a second quarter, that also gets rounded away, and we end up with a final result of 2. However, if instead we add the 2 quarters together first to get 1/2, if we add 1/2 to 2, then our end result is 2.5. So this is another example where floating point addition is not associative. While each of the individual additions was rounded according to round to nearest, for the aggregate operation, the result depends on what order you add them up. Now we'll get back to completing floating point arithmetic to fill in cases where some of those values aren't defined. This is analogous to what's seen in the mathematical systems throughout our educations. For floating point, the additional values we're going to add are positive infinity, negative infinity, nan, not a number, and -0. So just briefly, infinities act more or less how you would expect. Nans can be a little surprising when you first see them. The most surprising thing about nan is that a nan is neither less than, greater than, nor equal to any value, including itself. This is very surprising, but it is a conscious design of the IEEE standard. These are the IEEE standard rules for special value arithmetic, and these rules are also used by the Java platform for those cases. So we've said that the floating point arithmetic approximates real arithmetic, its values, and its properties. So we've seen it can only represent a small fraction of the values. How about the properties like the field axioms? Well, most of the field axioms don't hold for floating point arithmetic. The ones here in orange do not hold. So we've seen, for example, that associativity doesn't hold. The reasons these field axioms don't hold are due to round off, and they're also due to the handling of the special values. So there's very few transformations you can do on floating point expressions and still preserve the same answer. With that, we'll move on to understanding more about the floating point approximation. So first question to ask, is the approximation deterministic, reproducible, predictable? It can be. IEEE 754 does precisely define the results of operations on specific values. CPUs and the Java virtual machine usually defer to the IEEE standard for the corresponding instructions. However, there are various confounding factors. As we've seen, the field axioms largely don't hold, so many optimizations change the computer result. This doesn't just hold for optimizations. If you change an expression to one that's algebraically equivalent, it might not be equivalent under the rules of floating point arithmetic. There's often a laxity in the mapping from language level floating point operations to hardware instructions. That can change the results. And often library functions are not tightly specified. That isn't necessarily a problem. Often you want different behavior from composite operations on different platforms, say, to run faster. There are also many vagaries in binary to decimal conversion. What you see is not what you get, and that's what we'll look in next. So integers can be exactly represented in any base. In general, fractional quantities exactly representable as a finite string in one base cannot be exactly represented as a finite string in another base. For example, in base 10, 1/3 is a repeating fraction, 0.33333. However, if we use base 3 instead, 1/3 is this 0.1. It's a terminating fraction. Many of the floating point surprises we see are related to issues converting between binary and decimal. So let's see what happens when we try to convert 1/10 to a binary fraction. We start running the conversion algorithm here. So the first digit we get is 0, the next digit 0, 0, 1, 1. And now we notice that in the conversion algorithm, we get repeated state. We're going to cycle repeating 0011 ad infinitum. So this is a repeating fraction in binary. 0.1 in decimal is a repeating fraction in binary. So this has a number of implications. One of those implications is that the float approximation to 0.1 is not equal to the double approximation of 0.1. Why is that? Well, float has 24 bits of precision for its approximation, and double has 53 bits. So if you have 24 bits to approximate 0.1, you'll have some number of repeats of 0011. And if you have a 53-bit approximation, you can fit many more repeats of 0011. So they're not going to be the same. If we look at the exact value of the float approximation to 0.1, we see that it matches to the first 8 digits, which is about what we'd expect from a float, because a float is good for about 6 to 9 decimal digits. If we look at the exact decimal value, the exact mathematical value of 0.1 as a double, we see that it's good to 17 digits, and that's about what we'd expect, because a double is good for about 15 to 17 decimal digits. So the double approximation is more accurate than the float approximation, and it's not the same as it. Now, how about going in the other direction? How about we go from binary to decimal? We actually don't have the exactness problem, because it turns out all binary fractions are exactly representable as decimal fractions. And the reason for that boils down to that 10 is 2 times 5. So if we look at converting binary fractions to decimal, 2 to the minus 1 is 1/2 or 0.5. So it looks like that's getting pretty long, pretty fast. So how about if we look at the double dot min value, 2 to the minus 1074? How many digits does that require? It requires a lot of digits. It requires still more digits. It requires over 700 digits to capture this value exactly. Although it can be done, it is exact. So this would be rather unwieldy to work with. So maybe there's something else we can do here. What properties do we want the decimal to binary conversion to have? What we'd really like is if we start with a binary floating point value, convert it to decimal, and then convert it back to a binary floating point value, we get the original value back. That would allow us to use text reliable information exchange. But to do this, an exact value is not necessary. The decimal to binary step intrinsically deals with imprecision rounding. So our approach here is to use an inexact decimal string for output, but one with enough precision to cover the initial value. So as we saw before from the rounding example, there are the whole region of the number line that will round to a given floating point value. So which string representing that number should we choose? Why don't we have a rule of choosing the shortest string, which rounds to the value? And this is a general mathematical trick. When you have many possible answers or an infinite number of answers, impose some side conditions to define a unique answer. So how long should that string be? Again, it goes back to the differing precisions of float and double, 6 to 9 digits to float, 15 to 17 for double. So from a round trip here, from going from binary to decimal, we use the shortest string, which is generally inexact. And then we use the round to nearest rounding from decimal to binary. And even though both of these components are themselves inexact, the composition of them is exact. It's the identity function, which is surprising, but it's certainly very convenient here. So when you see a decimal floating point string, think of its nearest binary neighbor instead, because that decimal value probably isn't entirely. So let's say we want to add up 1/10 10 times. What does that equal? Well, it depends. If we just have the simple summation here and run it, we get something ever so slightly less than 1, although it is about as accurate as we expect from float, from double, excuse me. Let's say instead we add up these 10 copies pairwise. A pair of 0.1, then add that to the sum of another pair of 0.1. If we do it in that order, now we get 1. So this is another instance of the floating point sum, depending on the order the summation is taken, because the underlying addition operator is not associative. So if there's multiple orders we could do the summation in, how can we pick the best one? Are there ways we can get some more accurate summations than other? And there are. We can sort the inputs, adding the small magnitudes to each other's first to reduce round off. We can also use more intermediate storage, and we can use higher precision for intermediate results. Again, usually using more precision for intermediate results gives you more accurate answer at the end. Now, IEEE arithmetic isn't the end of arithmetic. There's other sorts of things you might want to use. You can use IEEE as a building block. For example, you can build higher precision arithmetic on top of IEEE, things like software quad. And you could do that either with clean rounding or sloppy rounding. You could build complex and imaginary numbers in various ways. You could work on intervals. Instead of dealing with points, you deal with ranges of numbers and put those together. So in the future, after Project Valhalla features on JDK, it'll be more attractive to explore adding different kinds of numbers to the Java platform, since they'll have faster support at that point. So a few lessons for floating point for your numerical programming. One is knowing when to expect exact results. And by default, you should not expect floating point results to be exact. You should expect them to be close, but not exactly equal to the mathematically exact result. If certain extra conditions hold, exact results can be expected. So if you're working on integer values within the range where all the contiguous integers can be represented, that can be exact. Multiplying by powers of 2 can be exact. There are certain special algorithms for extending precision that can be exact as well. Finally, the math library has certain cardinal values that are documented to have a particular behavior. So for example, sine of 0 is exactly 0 in the specification. And we augmented that list slightly in JDK 17. A corollary of that is be careful when using floating point for monetary values. One reason for this is the decimal to binary conversion issues we've seen. If you're trying to store $1.1 or 1.1 euros or 1.1 of some other currency, that won't be exactly representable as a floating point value. So what can you do instead? You can multiply up to cents or mils or whatever smallest unit you're using and store an integer. If you do operate on the mils or cents, be aware of range limitations, or you could also use a type like big decimal that can store decimal fractions. Another thing to watch out for is checking for equality. Sometimes it is fine to check for equality. It's usually a little suspicious. One case it's okay is avoiding divide by 0. However, if dividing by 0 is bad, dividing by a small number usually isn't very good either. So if you're not careful, it'd be easy to write an infinite loop in floating point. For example, this while loop here is infinite because you never quite hit 1.0. So if you want to use a counted loop, use an integer loop count instead. And if you want to base loop termination on the floating point sum reaching some value, use one of the ordered comparisons. That's a more robust way to do things. So if we have a simple summation code like this, what does it mean? What are the code semantics? So in the Java language, the addition operations must occur in the order they're written using the known data types. This is strong operational semantics and gives a lot of predictability. Other platforms make different choices in those regards. And in the Java platform, if you want to explicitly opt into more optimized or more platform-specific behavior, you can by using various library methods. For instance, the streams library, you could call a method like doublestream.sum, or now in JDK 17, you could use the vector API, which is currently in preview. You may have seen the feature list for JDK 17 includes JEP 306 to restore always strict floating point semantics. What's that about? This is a small detail most Java programmers don't need to be aware of. Between Java 1.2 and Java 16, for some rare cases on popular processors, a little bit of variance from the exact floating point results were allowed, but that variance is no longer needed or helpful, so we got rid of it in JDK 17. So floating point is a practical and pragmatic system for approximating real arithmetic. Behavior may be surprising, but there is an underlying order and design. And even if you don't like floating point, hopefully you're more comfortable with it after this talk. So thanks for attending.